Lee Harrison and Kang Lee are going to be presenting Arms Race, the story of insecure bootloaders. And with that,
first, thank you, ShmooCon. My name is Kang Lee. I attended ShmooCon a few times before, but this is the first time speaking. And also, here's my co-speaker, Lee Harrison. We are here try to come to talk about the secure bootloading. Also, you might think about it as insecure bootloading. Okay. Before I start, I want to first talk about the mobile device ecosystem. So in this ecosystem, we have the following players. Device manufacturers, and these are the system builder and the manufacturers for the mobile device. For example, Samsung, Apple, and Qualcomm. And there's also the service providers, for example, AT&T and Verizon. The other part, the large part of the ecosystem is actually the customers, us, like you and me. We are the device owners. I put a code there, we are the owners, but later you'll see we are also the potential, the so-called attackers. So why we need to look at the bootloaders? In fact, what we try to do is to show you how to deal with lots of the lockdown happening in this ecosystem. There are different levels of lockdowns. And we often use the term, you probably heard the term, I'll use the term root or jailbreaking a lot. But in practice, there's actually multiple levels of, you can say, jailbreaking happening or lockdown happening. So at the very top levels, people, most users want to say, I want to install some application and I just want to need a root to the system. But if you go lower layer, say for users, even you have root, it doesn't mean you can install a new kernel. So if you want to install a customized Linux kernel, it might need additional effort. And later, like even you have a customized kernel you install, it doesn't mean you can change the bootloader. So sometimes you might have to go even lower to try to help you break the higher level lockdowns. So in general, whenever you have a lower level lockdown you broke, in general, it will be easier for you to get upper layer. So in this talk, we're going to focus on the lower part. So we look at bootloader, mostly try to see how to run a customized kernel, or sometimes we also need to try to modify the bootloader, try to help to install the customized kernel easier. We're now going to talk about how to get root access to your phone. Okay. Now, I have a few disclaimers first before we go to the talk. I want to lower your expectation a little bit. In this talk, we're not going to disclose any newly discovered bootloader flaws. We are actually we are collaborating with a few mobile providers, so we are not allowed to talk about anything new. And in fact, I don't think we have anything completely new yet. Okay, and all the bugs we present here has already been patched, at least in the device we're going to talk about. And all the bugs are found independently by us. Just one example, we're going to show about 6 bugs, but one of them, there's a group, they actually disclose this. They find it simultaneously with us, they actually communicate with us, but they disclose it first. Okay. We'll make that clear in the later slides. With all these disclaimers, then you might say, hey, why do you want to make the talk? We already know all this. Okay. The important thing is bootloader security is really unique and fun. Okay. So why I say this thing is unique? First, when we look at the software, when we reverse the software, we can sense that all this software was developed under huge time pressure. I understand like lots of the software products have the same issue. It has to ship to the market. But on the mobile market, this is really critical. And if they miss a deadline, what I heard is that they're going to miss, they have to have huge penalty payback to the service provider. So that's one unique part. The other unique part is that the threat source. As I mentioned earlier, we all have mobile device, and you are the attackers that they are trying to prevent against. Okay, so the owner are one of the potential attack source, and in addition, it's different from other, lots of other security problems. is that you have the physical access. So it's sort of unconventional to lots of the software security we look at on the internet. Another aspect of this is that based on the bugs we find, some of the bugs are not really conventional. You might play a lot with memory vulnerability, double free. You play with a lot of those. Well, that's not what we see here. Okay. So with that, I'm going to first give you some basic introduction about the terminology on the pieces related to this talk. I show a phone here. This is actually the back side of the Samsung S4, one version of it. There are parts are familiar with probably by all of you. Like, for example, I show there's a SIM card. You can put a card there. There's also external flash card you can put in. You can put your music, movie, whatever there. There's a few other pieces that's important, but it's really hard for us to pinpoint where it is. Some of these are in the SoC chip. Some of that really probably hide, deeply on the circuit, and you cannot remove it. So one example is this eFuse. eFuse, you can consider these are write once memory. So you can only write it once. Okay? And on these eFuse, you have all this phone-specific, individual phone-specific numbers, like, for example, serial number. And most of you probably run into this, like, if you upgrade your phone, the patch is going to blow some of the fuse, and that's not reversible, so which means like it's hard for you to downgrade. Okay? So there are lots of other information there. Another important piece is this eMMC is an internal flash. You can consider this really like the same as your flash card, although it's just like it's a piece of memory that it's very hard for you to pull out. Okay? On this card, it has it's really a disk. You have the partition table, you have all the bootloader, the later stage of bootloaders saved there. You also have the kernel image stored there. Another related piece is the ROM. This is a read-only memory. Like when you power on your phone, the code you start is come from there. Okay? So the prime bootloader is from there. Now, with that, let's look at the very generic view on how a phone boot. So this is a high-level view of a bootloader, how it works, and later you will see individual phone how it works for each type we bring here. So when you power up, as I mentioned earlier, that your ROM going to get executed, the code come from there. That piece of code is going to look at the flash and find the first stage of bootloader and run from there. And obviously, before it run it, I always check the signature of that code. If it match with the vendor built-in or whatever specified by the code, then it will hand it to that new stage of bootloader, then run from there. This might go through multiple runs, and you will see this later. And at the end, the last stage will then read the kernel, let's say Android Linux kernel, then get it run. Now, here's a quick overview about how the bootloader works. And basically, this goes through multiple runs, and I have a really simplified version. Let's say on the right side, you already have a lower level bootloader running there. What it does is it's going to read the next level bootloader and try to load it in memory. But before it handed the execution over to the next level, it will double check some of the signature. So on the disk, for the next level bootloader, it's certainly there's a file, you can consider our partition, store this. It has header, has the code, the image there. There's also a signature. So what this current level bootloader going to do is it's going to read the code into memory and then do a hash. It's going to get another hash out from the signature by decrypt it with there's a public key probably buried in the current level bootloader. Only when this hash match, then it will proceed, hand it over to the next level bootloader. So this is a really high level overview. Now, with all this background set, we're going to enter a few case studies. So the very first one we played with is this Samsung Galaxy S3 that's been released about 1.5 years ago. And what it uses is a Qualcomm chip. So our goal, the first thing when we play with it is try to just put a customized kernel image. Okay. Now, if you look at the bootloader, the whole boot process for this S3 phone, it starts from ROM. This is come from the read-only memory, and it's going to read in multiple level bootloader, and this, the SPL 1 to 3, and also the later A boot, all stored on the internal flash disk. And each level going to verify the next level before it hands the execution over there. And you can see that SPL1, SPL2, 3, and each load the next one. And each of this bootloader actually has its own task. For example, the SPL2 not only load SPL3, it also load other components, like for example, the power, resource management, and the trust zone. What we're going to focus on for this talk is we're only going to focus on how to put the customized kernel, so the trust zone, which is a very important part, very interesting, but today we're not going to talk about it. Okay. So we're going to focus on the A boot. Now, remember, our goal is try to load a customized kernel. So if we can trick the A boot, they are doing some verification. If we can trick the A boot to load our kernel rather than the stock kernel, then we achieve our goal. So we look at how the A boots verify the kernel image. So what we did is really get the binary from the flash. We don't have the source code. So put in IDA with a little bit tweak, then we have the pseudocode. And when you look at the pseudocode, when you have the decompiled C code, then we figure out that the A boot actually checking does the following. It loads the kernel image into memory twice. So first it copy to the place that it wants to execute it, and then before it jumps there, it will make another copy to a scratch memory and do the verification there. And then if it passes the verification, then it will jump. Now, give you a little bit more detail. The data are read from the disk, the internal flash, and there's a partition table. And each of the, there's multiple partition, and the kernel is in one of the partition, it's called boot. Okay? And this is very similar to your hard drive partition table, although it's on the flash. Now, more detail. Here we bring the pseudocode of the. How did you get the code? How did you pull off the flash? Right. In the S3 case, it's actually that section is readable. We will later talk about, depending on which phone, some of the boot section is not readable. So this part is readable. The protection rely on, if you modify it, you need to have the right signature. Okay. Now, if you look at the code, here are the really simplified version. The loading effort first. It basically search the partition, find there's a partition called boot, then copy it into memory. Okay. Then on the right side, on the green box, we have the verification stage. It's same thing. You go there, look at the partition table, check whether it's boot. Okay, then verify. If it's good, then later jump to the one that loaded by the blue. Now, for those of you who have sharp eyes, you might already notice. Okay, there's some problem. Okay, and you're right. So the difference is like there are two string comparison, but there are different one. One is string copy, which is case sensitive. The other one is case insensitive. We suspect this actually come from different developers. One guy is writing the code, and the other one adding the checking. And now, like for this audience, it's obvious. Like we have an easy exploitation. Okay, now we will get more complicated stuff later, but one thing I said unconventional is that lots of time you just have this type of simple bugs, right? Now the way you claim victory is the following. You create two partitions. One is called boot, the other one also called boot, but one is case, capital, the other one is lowercase. So at the end, what happened is that the one load is our kernel, the one being checked is the other one. Okay? So you can go ahead like check which one you want to put first, but because of time issue, we just move ahead. So we have a small victory. Of course, Samsung respond very quickly. They patch it. They actually just loaded it once, so there's no mismatch anymore. So let's look at the next case. Now we actually start looking at the Note 2. This is also a phone released fairly recent, about a year. This time it was not using Qualcomm chip. It's actually using the Samsung their own chip. Okay, and we still have the same goal. Okay, we want to put the customized kernel. We want to trick the latest stage of the bootloader and to try to say, can we do something? And This is a detailed boot loading process for the Node 2. And you can see that the boot process actually changed a little bit. And for the Samsung's, their own chip, they don't use the A-boot. They have this chain called BL1, BL2, BL3. And overall, this chain is called S-boot. It's actually in the S-boot section. Okay? And because our goal is try to load the kernel, obviously, let's focus on the last stage of bootloader first. Okay? Then we did the same thing. This time we get the code and we look at it. And this is how they load the image. So eventually somewhere they will check, okay, so this is an image that has a magic sequence of Android. Well, we're going to load in kernel and copy. I know, like, because I showed you early slides, you're probably still looking hard, try to see where's the trouble. We actually look hard here, and in this section, it's actually not much problem. They load the kernel, they copy this, then later they jump to that place to run. What I didn't show you, and in fact, when we look at closely, we actually find there's else branch. Okay, so again, if you're like, oh, it's trivial, okay, and there's else branch if you have a image you try to load, it doesn't have the Android sequence. What the bootloader does is it just jump there. Now it doesn't do lots of the setup. It just jump there and run. Okay. And now you say, oh, this is trivial. See, part of the talk is trying to tell you actually, bootloader sounds complicated. It can be a simple bug. Okay. So you have this flash RAID. All you need to do is prepare the code put there, and they will run. And so we have this small victory. Okay, we have this else branch, probably debugging patch or something help us to run. However, this bug happened there is really very primitive, like in the sense that when you try to load the kernel, the lots of setup work need to be done, and all you have is like you have an ability to jump to your code. You can actually write your own bootloader and maybe use a customized kernel and run there, but you need to do lots of setup. What we really want is we want to leverage the original bootloader. We want to modify it rather than just develop everything from scratch by ourselves. So for the complicated stuff, then I'm going to let my co-speaker Lee to handle it from here.
All right, so we can load a kernel. We'd have to write our own loader. That's kind of a hassle. So let's see if we can modify the early bootloader stages, see if we can avoid having to write all that code and just be able to simplify the kernel loading. So first we'll look at, well, what happens if we change the bootloader? So we initially encounter the problem, the bootloader is signed. Any modification we make will obviously break the signature. So how can we solve this? To do that, we're going to first look at how the first stage bootloader is verified from the ROM. And we find that the boot ROM actually uses a fixed key in part of its verification process. And we realize this can help us. Because after looking at a couple devices, we realized the same key was used across all CPUs of the same model. So every Exynos 4 device used the same key in the CPU. Well, how can that help us? Well, it turns out we found this one hobby board, the Odroid X, that actually ships with a first stage bootloader that does not verify the signature of the second stage. So this is a pretty big hole. So from here, we can actually make a custom bootloader. So if we take their first stage bootloader, we can glue it with the second and third stage from the original device, say the Node 2. And if we put that together, we can create a bootloader that the device will load, verify, and then run. So this is pretty good so far. But the problem here is the bootloader partition, unlike on the S3, we can't read and write to this partition. Android cannot actually see where the bootloader is stored. So we're going to have to get around this. To do that, we're going to look at how the bootloader is stored on the eMMC chip, on the internal flash. So the bootloader is stored on the boot 1 partition, the first one in kind of orange there. Android can only see the blue partition, the user data, as it were. So we need to find some method to write to this new boot 1 partition. and replace the existing bootloader. So obviously, how do we do that? So then we remembered, wait, all these devices have to be updated in case they find flaws just like we have. So in that update process, they also have to update the bootloader. So the firmware update mechanism has a way to write to this partition. So the phone has a special download mode that it boots into. It's not the same as booting up into the full kernel, say Android. But it lets you see everything. It lets you flash to this boot1 partition. But like any good flashing program, it does also check the signature, which if we try to flash our cobbled together custom bootloader, it won't verify. So we need to find a way around this signature check. So we're very close, almost there. We just got to find one more thing. So we can disable that check. Because before we'd found an exploit that allowed us to load up whatever code we wanted, doesn't matter if it was signed or not, and then have the phone execute it. And that was that debugging else branch that we saw earlier. So using that, we can write some code that will run and kind of disable the checks in the current bootloader. So then when you put the phone into the download mode, all the security checks are gone. And so then the bootloader will let you flash our new custom bootloader to the device without any issues. So here we can claim victory because we've been able to install our own custom bootloader that now requires no modifications to the kernel when you boot. So you can take the results of the compilation process for the kernel and immediately throw it on your phone and it'll run, which is pretty good for us because that was our goal. All right, so they were very prompt, again, in fixing that issue because they removed that else branch. And they also added the blacklisting of older bootloaders, so you couldn't try to downgrade to the old version and then use the same exploit to install a custom bootloader back on it. So they've kind of beefed up the security, and we're going to have to find another hole. So obviously we need another method for putting our custom bootloader onto that boot partition. We can't remove the flash security checks anymore. So let's go back and take a look at the firmware update mechanism. So we know it's doing some checks. Before, we never really investigated the checks because we realized we could just remove them. So it doesn't really matter what they're checking, we could just patch it out. But now we actually have to care a bit. So what kind of checks are they doing? It's an RSA signature, very similar to the generic diagram we showed you in the beginning. So when are they doing these checks? Well, it turns out not every partition that gets flashed needs to be signature checked. And they actually have a hard-coded list of names. So only when you flash a partition that has the name that's in that list will it run the signature check. So then we can look, where does it get the partition information? So they have another structure, a partition information table, or the PIT. It's kind of a secondary table in addition to the GPT that we saw earlier. It just contains additional metadata they use for the flashing process. But luckily for us, the root user can edit this table. It's on the disk, the part of the disk that's visible to the Android OS. So here we see an example of the eMMC chip, the flash chip. We have the GPT at the very beginning. The PIT is not far after that. And then later on, we have the full boot partition, the recovery partition, and so on. We can zoom in on the PIT. We see the PIT has a header. The PIT has entries for each partition on the disk, just like the GPT. And these entries are going to have additional data like the partition ID, what file system type it is, and then they will also point to where the partition data is on the disk, along with the size and a couple other. So how are we going to use this PIT to bypass the flash check? So what we're going to do is going to create a duplicate PIT entry for the bootloader partition. But we're going to change the name. So because the decide whether to run the signature check or not based on the name of the partition you're going to flash, well, we'll just call it something else that's not in that list. But the key point here is we're going to have these two entries, the original bootloader entry and our custom bootloader entry. They're going to point to the same location on the disk. So here we have an original pit. It's got the boot entry that later points to the boot data. Now we have our custom myBoot entry. It's also going to point to the boot data. So the boot is on the list, so it's going to be signature checked during the flashing process. myBoot is probably not going to be on their list, so that won't be checked. But if myBoot is able to be flashed, it will flash to the same location as boot would have been. So we can use that trick to flash our custom bootloader back on the device. And that did work, and we were able to get it back on there and then boot custom kernels once again. And we're going to hit this poor note too one more time at a lightning round. So in a subsequent update, they added a signature check on the pit region at boot time. So if you turn on the phone and the pit was tampered with, it won't boot up any further. It will force you to go into download mode. It won't let you exit until you flash an untampered pit. So they keep adding more locks. So we can't add our entry anymore. So we can't kind of bypass the mechanism. But the downgrade, we can downgrade, because even though they added this blacklist in one of the previous updates, they forgot that blacklist the previous version. So you could just flash back the one that was vulnerable to the pit attack and then use that. But this one was also fixed. So we're done with that note 2. And we're going to move on to the Galaxy S4. This one a bit more recent, about April last year. This is also based on a Qualcomm chip. So we're moving back to Qualcomm from the Samsung Exynos. And what's different about this one is that other carriers also asked to lock down the device, because in the past it's really been, say, Verizon that has wanted the phones to be very secure. But now, this is just AT&T are also asking, hey, don't let them boot custom kernels. But obviously our goal is still to boot a custom kernel. So we're going to bring this picture back. This probably looks familiar. It actually is the exact same boot flow as in the S3. This is very typical for the Qualcomm-based phones. And we're, again, going to look at the A-boot. So we're going to look at how A-boot is going to load this kernel into memory. So let's pretend we're running, the execution is inside A-boot. So the goal is to have A-boot load the kernel and the RAM disk into memory. So how it's going to do that? It's going to use this MMC read function. So the first thing it's going to do, it's going to read the beginning of the partition, read a header into just a local variable. Then it has 2 subsequent reads that are going to load the kernel and the RAM disk from that same partition. And this should put everything into memory. Now, knowing that, what can go wrong? So there's a very big hole here.
I just feel like we already show a few really silly, not really complicated bugs. I just really try to see maybe some audience can point out what can go wrong. So this is not really difficult. We have time, that's why I pause.
Okay.
But no one responds.
All right. So there is something that can go wrong. So that header that it reads, who controls that? Well, you do. It's on the disk. You can write to the disk. And then what does it do for the second and third read? It uses information from that header to control where and how much data is loaded into memory. So it's only going to load the kernel to wherever you say to load the kernel. It's only going to load the RAM disk to wherever you say. So we can abuse that because these are user-controlled values. So hopefully you spot the problem. There's no input validation for the addresses, the size. If we change the address, we can load code anywhere, even on top of the bootloader itself. For this one, yes, you would need to be root to be able to write to that partition directly. But yeah. So we're going to change the loading process a bit. We're going to have the second MMC read, the first, or that originally just loaded the kernel. We're going to have it load a combined kernel and RAM disk because we need that third read to load up some code. That code is going to actually overwrite the signature check function in the bootloader. So later when the bootloader loads up all the code, it tries to call the function to verify it, well, it'll actually call our custom code. And our code can just say, sure, that's all right. This one was first published by security researcher Dan Rosenberg, so good shout out to him. This also affects many other vendors, like LG. A lot of LG phones can use this too. So to illustrate the exploit, so we have the first MMC read. It's loaded the header into the RAM. The second MMC read is going to load our combined kernel and RAM disk. And then the third will load our patch code directly on top of the bootloader. So we can control how the verification happens in the bootloader now. All right, that's enough for that exploit. I'm going to pass it back to. Okay.
So I'm going to summarize this. So there's actually a bunch of vulnerability or bugs we mentioned. I have the list there. I'm not going to go through each of this. But yeah, since it's really a quiet audience, I want to summarize the following way. So my experience, my view on this is that when you have the hardware, when you own the device, when you're also able to modify lots of it, this is like, lots of problems actually are input validation problem, not really like memory vulnerability. So this is like really like you need to do SQL injection, but you also own the SQL database. Okay, so that's so what I'm trying to say is that the bootloader, although it's it sounds complicated, but the attack, since you have the advantage, you own the stuff. There are lots of things you can do, and also this, I guess, says the other way. If you want to secure the bootloader, it's really difficult. That's why I say most of these are not necessarily the conventional vulnerability. And so from the vendor point of view, it's pretty difficult for them. And I also want to say that the problem are not limited to Samsung. We show a few examples with Samsung. That's because we have access to the device, and also because they actually acknowledged and patched it. The rumor says that actually some of our bugs still available for other devices. I cannot say that. But at least here, for all the bugs we showed, they've already been patched. But at the same time, you can tell that because of this type of simple bugs, it means that all of you, if you're interested, you might have to jump on and work on it. Okay? So on the other hand, when we talk to the vendors, we actually know that vendors are very open to let you put your customized kernel. As long as you buy a device from them, they will be happy. So very often the request for lock down the kernel, lock down the device is often come from the service provider. This is because of their business model. So with all that said, I want to conclude the talk basically saying, this is a good experience. This is our story about going multiple rounds of working on the bootloader, work it, get it patched, and work it again. So you guys, if you have questions, we're more than happy to answer. I haven't done any work on Apple. I think obviously we want Apple maybe donate more hardware, then we will play with it. Obviously, I don't know, Lead, have you?
I have not.
No, he said no.
Have you done any research on Samsung Knox?
We actually, in the process, try to get the software, and we have the hardware actually able to run Knox, but Knox was targeted for enterprise customers, and we need to get the access to the software. We're in the process of getting it.
One of the other things in our research that was suggested is the Samsung EQ stuff. It's been suggested that it's really not an EQ, they change the JTAG.
Right. So yeah. So the question is, if the eFuse are now real eFuse that is supposedly write only once, if you can reverse it, obviously, if you can do that, that saves lots of dead phones, and we're definitely more than happy to hear, how to do it. We don't know about it, and I heard the rumor, but I never, able to get. Okay. Thank you.
Lee Harrison and Kang Lee are going to be presenting Arms Race, the story of insecure bootloaders. And with that,
first, thank you, ShmooCon. My name is Kang Lee. I attend ShmooCon a few times before, but this is the first time speaking. And also, here's my co-speaker, Lee Harrison. We are here try to come to talk about the secure bootloading. Also, you might think about it as insecure bootloading. Okay. Before I start, I want to first talk about the mobile device ecosystem. So in this ecosystem, we have the following players. Device manufacturers, and these are the system builder and the manufacturers for the mobile device. For example, Samsung, Apple, and Qualcomm. And there's also the service providers, for example, AT&T and Verizon. The other part, the large part of the ecosystem is actually the customers, us, like you and me. We are the device owners. I put a code there, we are the owners, but later you'll see we are also the potential, the so-called attackers. So why we need to look at the bootloaders, help to install the customized kernel easier. We're now going to talk about how to get root access to your phone. Okay. Now, I have a few disclaimers first before we go to the talk. I want to lower your expectation a little bit. In this talk, we're not going to disclose any newly discovered bootloader flaws. We are actually we are collaborating with a few mobile providers, so we are not allowed to talk about anything new. And in fact, I don't think we have anything completely new yet. Okay, and all the bugs we present here has already been patched, at least in the device we're going to talk about. And all the bugs are found independently by us. Just one example, we're going to show about 6 bugs, but one of them, there's a group, they actually disclose this. They find it simultaneously with us. They actually communicate with us, but they disclose it first. Okay, we'll make that clear in the later slides. With all these disclaimers, then you might say, hey, why do you want to make the talk? We already know all this. Okay. The important thing is bootloader security is really unique and fun. Okay, so why I say this thing is unique? First, when we look at the software, when we reverse the software, we can sense that all this software was developed under huge time pressure. I understand lots of the software products have the same issue. It has to ship to the market. But on the mobile market, this is really critical. And if they miss a deadline, what I heard is that they're going to miss, they have to have huge penalty payback to the service provider. So that's one unique part. The other unique part is that the threat source. As I mentioned earlier, we all have mobile device, and you are the attackers that they are trying to prevent against. Okay, so the owner are one of the potential attack source, and in addition, it's different from other, lots of other security problem, is that you have the physical access. So it's sort of unconventional to lots of the software security we look at on the internet. Another aspect of this is that based on the bugs we find, some of the bugs are not really conventional, You might play a lot with memory vulnerability, double free. You play with a lot of those. Well, that's not what we see here. Okay. So with that, I'm going to first give you some basic introduction about the terminology on the pieces related to this talk. I show a phone here. This is actually the back side of the Samsung S4, one version of it. There are parts are familiar with probably by all of you. Like, for example, I show there's a SIM card. You can put a card there. There's also external flash card you can put in. You can put your music, movie, whatever there. There's a few other pieces that's important, but it's really hard for us to pinpoint where it is. Some of these are in the SoC chip. Some of that really probably hide, deeply on the circuit, and you cannot remove it. So one example is this eFuse. eFuse, you can consider these are write once memory. So you can only write it once. Okay? And on these eFuse, you have all this phone-specific, individual phone-specific numbers, like, for example, serial number. And most of you probably run into this, like, if you upgrade your phone, the patch is going to blow some of the fuse, and that's not reversible, so which means like it's hard for you to downgrade. Okay? So there are lots of other information. In fact, what we try to do is to show you how to deal with lots of the lockdown happening in this ecosystem. There are different levels of lockdowns. And we often use the term, you probably heard the term, I'll use the term root or jailbreaking a lot. But in practice, there's actually multiple levels of, you can say, jailbreaking happening or lockdown happening. So at the very top levels, people, most users want to say, I want to install some application, and I just want to need the root to the system. But if you go lower layer, say for users, even you have root, it doesn't mean you can install a new kernel. So if you want to install a customized Linux kernel, it might need additional effort. And later, like even you have a customized kernel you install, it doesn't mean you can change the bootloader. So sometimes you might have to go even lower to try to help you break the higher level lockdowns. So in general, whenever you have a lower level lockdown you broke, in general, it will be easier for you to get upper layer. So in this talk, we're going to focus on the lower part. So we look at bootloader, mostly try to see how to run a customized kernel, or sometimes we also need to try to modify the bootloader, try to